Next topic is ignition system. The function of ignition system is to provide necessary energy to initiate the combustion process. There are several types of ignition systems. We have a capacitive discharge ignition system or CDI system. So in this system, the capacitor is used to store the ignition energy. And then we also have what is called induction ignition system. So instead of capacitor, an induction coil is used to store the ignition energy. This figure is showing an example of induction ignition system. So on the right side is the layout of the system. So in this induction ignition system, they have a battery as the energy supplier, and then coil. Next one is the spark plug, and number 4 here it can be it's control unit, and then number 1 here is a kind of ignition lock. And then the feature on the left side is showing the circuit layout. So we have a battery to supply the electric energy. So in this case we have 12-volt a battery, so the current can be several ampere, and then this energy is flow into the induction coil. And then the function of this induction coil is to increase the voltage from 12 volt to be kind of like 5,000, 6,000 volt. So we need to have a very high voltage to enable spark discharge between the spark plug electrode. Okay, and this is the spark plug electrode. So the supplied energy to the spark plug can be only several millijoule, so it's very small. However, because the energy is delivered to a very small zone, so let me put a purple color to this, a very small zone. So this is between the electrode of the spark plug. We will have a very high temperature in this purple zone. So at the beginning of the spark ignition process, the gas temperature in this spark plug cap zone can be above 10,000 degrees C. Okay, we need to have a very high temperature to initiate the combustion process inside the spark ignition engine. This feature is showing the cutaway of a spark plug. The main component of the spark plug is the J electrode, or sometimes called a ground electrode. So this electrode is connected to the ground side of the electric circuit. So usually it is connected to the engine block. And then we have a center electrode, so the second electrode, and it is at this cap we have the spark discharge. And then other component we have a terminal nut, and this one is the extension of the terminal nut, and this is insulator. And then we have other insulator, so like a sealing, this one internal sealing, this gasket. So you can get this spark plug easily at any car shop when it's pretty cheap. You can get it by several bucks to get one spark plug. Spark plug. This component is used to convert high voltage electrical energy into the ignition discharge. So the spark plug is available under a different design. This feature is showing several different spark plug design and their lean operating limits at 2000 RPM and then 280 kilopascal net IMEP, and then with a moderate tumble and the COV IMEP of 7%. So the parameter that we will compare is the electrode gap. So this is the distance between the J electrode and the central electrode. And then the spark location X. So this is the distance between the spark plug body and the central electrode tips. And then next one is the drawing for each type of the spark plug or each design of the spark plug. And then the last row here is the lean limit. Let's take a look one by one. On the first spark plug design here, we have what it's called spark plug type of J. So it's called J gap spark plug. So this is the most popular design of the spark plug. You can get it easily in any car shop. So usually this J gap spark plug has an electrode gap of around 0.8 millimeter. And then the spark plug location X is 3.5 millimeters. This spark plug design has a lean limit of 1.57. So this is lambda. And then the next one is a J gap spark plug, but with a deeper spark location. You can see that it has a much larger spark location X here. It's 9 millimeter. The gap size is 0.8 millimeters. This spark plug design has a lean limit of 1.5. The next one is spark plug with circular electrode. You can see there they don't have the J type electrode. So the electrode gap is around 1 millimeters. And then the location here, you can see it can be 5, 2, or even a 0. And then it has the lean limit of 1.47. The next one here is surface gap spark plug. So actually this is a kind of a J gap spark plug, but it has more than one J electrode. So you can see from this picture, at least we have 2 J electrodes. So you will have a multiple spark for this spark plug design. And it has a lean limit of 1.51. The last one here, this is also J-gap spark plug, but the material here is platinum. So platinum has a better thermal durability compared to the other material type of the spark plug. And this spark plug design has a thin electrode, so you can see that the size of the center and the J electrode is relatively smaller than the first type of first design of the J gap spark plug. The purpose of having thin electrode is to reduce the wall heat transfer from the ignition energy to the electrode. So thus we have more energy to ignite the mixture, and it has a better ignition process compared to the production J spark plug. And this J gap spark plug with thin electrode has the highest lean limit, so 1.67, which is good. So the higher lean limit is, the better the spark plug is, and that it means that the spark plug can work under a linear mixture condition, and linear mixture required more ignition energy than stoichiometric mixture. Next topic is abnormal combustion. In spark ignition engine, we have knock and then surface ignition. These abnormal combustion phenomena are of concern. When severe, they can cause major engine damage. I have an example of the engine damage due to this abnormal combustion in the next slide. And if even not severe, they are regarded as objectionable by the engine or vehicle operator. Knock is the name given to the noise which is transmitted through the engine structure when spontaneous ignition of significant portion of the end gas occurs. So this spontaneous ignition occurs ahead of the flame front. So it adds ignition energy, or it adds energy release in addition to the energy release inside the flame front. And then surface ignition is ignition of the fuel-air mixture by a hot spot on the combustion chamber wall. It can be due to a debris attached to the wall, and similar to knock, it adds energy release in addition to the energy release inside the flame front. This picture is showing the schematic of auto ignition that can produce knocking. So assuming we have the ignition process from the right side, so this can be a spark plug gap, and then there will be a flame front propagation represented by this blue line. Okay, so it's mean here we have a flame front propagation to the left. And then because of this flame front propagation and then combustion process, energy release, the gas pressure increases. It will compress the unburned gas. So this is the unburned gas. It will compress the unburned gas ahead of the flame front. And then the end gas temperature will increase as well. And at some point, this mixture temperature can be higher than the ignition temperature, and then there'll be an auto ignition. So this is spontaneous ignition ahead of the flame front. When we have sufficient mixture burned due to this auto ignition, it can generate a very high pressure fluctuation and thus generate knocking. So, knock originates through auto-ignition of portion of the unburned mixture ahead of the flame when one or more localized regions in the in-gas are compressed to sufficiently high pressure and temperature to spontaneously react. There are three modes of knocking combustion observed. So one is what's called deflagration. So this is the common mode. It's generally resulting from small exothermic centers with steep gradient. And this deflagration mode is similar to the normal SI engine flame propagation process. Second one is called thermal explosion. So this is characterized by larger centers with flattened gradients, and the pressure oscillations are moderate, and knock damage, if any occurs, is light. And then the last one here, what is called developing detonation. So this is the most violent knock mode. So it's occurring rarely, but it's generating large pressure oscillation with a potential for significant surface damage. This figure is showing an example of cylinder pressure versus crank angle of individual cycle for three different knock level. So on the left side, we have a normal combustion. So it means we don't have a knock for the feature on the left side. And then B in the middle here, we have a slight knock. So it means light knock. So you can start seeing the pressure oscillation here. So this is due to the auto ignition ahead of the flame front. And then on the last feature, see here is a heavy knock. So it has a very high amplitude of the pressure oscillation. So this is heavy knocks, and this is the operating condition. So 4000 RPM, and then the engine size is 381 cubic centimeters. So when the engine is run under heavy knocks for a certain period of the time, then it will damage the engine component. This figure is showing how auto ignition produces pressure oscillations within the engine cylinder, produce block wall vibration that is measured by an accelerometer, which produce a noise. In this case we use microphone. So we have auto ignition that will generate pressure oscillation, and this pressure oscillation will result in block vibration, and at the end we use a microphone to record audible noise. And the left side we have on the top here we have the pressure measurement using two transducer. Number one is at the side wall. So this number one is the pressure measurement that produces pressure oscillation here, and this one as well. And then the second pressure transducer is at the spark plug, so it has less pressure oscillation. So you can see there the line about the middle of this oscillating pressure. So this is from the transducer number 2. And then the next one here is the pressure oscillation, or it is a block vibration measured using accelerometer. And then the last one here is the audible noise measured by the microphone. This feature is showing examples of component damage from abnormal engine combustion. In feature A, we have damage on the piston. So this is a piston holding by pre-ignition. And then B here, you can see a piston crown erosion, this one. And this is also due to knocking. And then C here is the damage on the cylinder head gaskets. And this is a splitting failure due to heavy knocking. And then on the last one here, we have erosion of aluminum cylinder head. So it is view from the bottom side. So this is the valve, and so this one is the cylinder head. So you can also see the erosion of this cylinder head due to heavy knocking. Next one is fuel factor. The tendency to knock depends on engine design and operating variable which influence gas temperature, pressure, and the time spent at high values of these two properties before flame arrival. So the tendency to knock is decreased through reduction in the end gas temperature. So this knock tendency is strongly dependent on the temperature. And one of the parameters that represent this knock tendency is called ignition delay. So this is the time required for the mixture to increase the temperature from that corresponding temperature to ignition temperature. So lower temperature increases the ignition delay, so that if we want to reduce the knock tendency, we need to reduce the end gas temperature ahead of the flame front. And this end gas temperature can be reduced by decreasing the inlet air temperature or retarding the spark from MBD timing. So by retarding the spark from MBD timing, we will have a lower pressure, which result in lower end gas temperature. However, knock is a phenomenon that is governed by both engine and fuel factors. So this fuel factor is the anti-knock quality of the fuel. So the fuel which has a good anti-knock quality will have a longer ignition delay, thus less knock propensity. Individual hydrocarbon compounds vary substantially in their ability to resist knock, and this depending on their molecule size and structure. And their tendency to knock has been characterized by a parameter that's called critical compression ratio. And this is defined as the compression ratio at which, under specified operating conditions, the specific fuel compounds will exhibit incipient knock. This feature is showing the critical compression ratio, so on the vertical axis here, as a function of number of carbon atoms. So what we can see from this feature is that for paraffin fuel, increasing the length of the carbon chain increases the knock tendency. So you can see in here we have a 2C, and then when we have more C like 5C, then it has a lower critical compression ratio. And then for aromatic and naphthalene fuel, usually it has a higher critical compression ratio. Also, you can see from this feature, this is isooctane that is usually used to represent the gasoline. And then N-heptane, that is usually used to represent diesel. It has much lower critical compression ratio. Octane number. Practical fuels are blends of a large number of individual hydrocarbon compounds from all the classes of hydrocarbons. So we have a paraffin or alkanes, and then cyclanes or naphthanes, and then alkenes or olefin and aromatics. And this octane number is a parameter that is used to measure the fuel resistance to knock. So it's determine whether or not a fuel will knock in a given engine under a given operating condition. So the higher the octane number, the higher the resistance to knock. Octane number is not a single value quantity since it depends on the engine design and operating condition during testing. For the standard octane number scale, we use two hydrocarbons. Number one is normal heptane or N-heptane. So NC7816. So this normal heptane has octane number of 0. The second hydrocarbon is isooctane. So CH818. So it has an octane number of 100. These hydrocarbons were chosen because of the great difference in their ability to resist knock and the fact that isooctane had a higher resistance to knock than the gasoline fuel. So blend of these two hydrocarbons form a primary reference fuel, and this defines the knock resistance of intermediate octane numbers. For example, a blend of 10% N-heptane and 90% isooctane on mass basis has an octane number of 90. Several standard octane rating methods for fuel have been developed. Two of these are carried out in a standardized single-cylinder engines. Number one, we have what's called the research method. It's a follow ASTM D2699. The testing result of the standard is called a research octane number or RON. And then the second standard, it's called a motor method. So it's follow ASTM D2700. The testing result from this motor method, it's called motor octane number or MON. Okay, so we have RON and MON. In the motor method, the engine operating conditions are more severe. Therefore, MON is usually lower than RON. So these conditions are likely to produce knock. This figure is showing the comparison of operating conditions for research and motor method. So for the inlet temperature, the research method has 52 degrees C, while the motor method has 149 degrees C. And the inlet pressure is at atmospheric condition. And this is the humidity and then engine speed. Motor method has a higher engine speed. And then it has also a higher spark advance. And as I mentioned to you, this temperature has a strong impact to engine knock. Now you know what is the meaning of octane number. So when you purchase your car fuel, you can check what is the required fuel octane number by your car. So in the US, the octane number is usually the average of RON and MON. So this is RON plus MON over 2. In Europe, in Asia country, usually they use RON to represent the fuel octane number at the fuel station. This table is showing the RON and MON for a different fuel. So we have a gasoline. Here gasoline has a RON of 91 through 99, and then MON is 82 to 89. And then E10 gasoline, so this is the gasoline with 10% ethanol. It has a octane number of 96, RON 86, and then MON of 86. Another fuel that might be interesting here is methane. So methane is the primary component of natural gas. It has a RON of 120 and MON of 120. So natural gas has a better knock propensity than a gasoline. And then next one here we have alcohol. So we have methanol, ethanol. So they have RON of 109 and then MON of 89. Another parameter to represent the fuel octane number is the fuel sensitivity. So this is the difference between RON and MON. NOx can be expressed by having additive to the fuel. In the past, we have a tetraethylate added to the fuel. This figure is showing the increase in RON and MON as a function of the additive mass per liter of the fuel. So as you can see on this figure that RON and MON increases with the increase of the additive amount to the fuel. Due to its toxicity, this tetraethylate additive is not allowed anymore. In the US, the gasoline fuel is usually mixed with 10 to 15% ethanol. Therefore, we have E10 or E15 fuel. How does this ethanol influence the gasoline octane number? This figure is showing the dependency of research octane number, RON, to the amount of ethanol in percent by volume. We have a different gasoline fuel here with a different octane number. So we have 98, 92.9 RON based gasoline, and then 91.5, and then 84 RON based gasoline. As you can see on this figure that ethanol increases the RON of the gasoline. So gasoline with a lower RON get a more benefit for the RON increase due to this ethanol fuel. Okay, we have completed this chapter 9 discussion. We can review this topic again in the next class meeting. Thank you and stay safe.